So good morning. So today we will continue with the steady state cornering. In the last class, we looked at essentially a model called the bicycle model, which is a very popular model, yaw plane model of two-axle vehicle. So commonly passenger car vehicles are represented by bicycle model in order to study its handling characteristics. So handling characteristics means you know that what is the responsiveness of the vehicle for the given input by the driver. The given input by the driver essentially not only acceleration or braking and as per the need, most importantly maneuverability by steering. So when he gives a steering input, is the vehicle listens to him or not, is what is essentially responsiveness of the vehicle. And essentially this type of understanding study is what is called vehicle handling studies, otherwise called a lateral dynamic study. By looking at the observation of motion of vehicle, you can say that's 2D motion on the ground, because it's not going to go in a straight line, it is going to go in a curved line. So that can happen by the input by steering, or it can also happen when a vehicle goes in a straight path and there is a sudden disturbance in the side way by wind gust. Then there can be a side force disturbance that would also create a situation that there is a necessity of lateral force to be developed in order to ensure the stability of the vehicle. So at that time also you would see that the characteristic of the vehicle, how does it respond, is going to be ranking the vehicle classes, right? Because the stability is what is very important in such cases, and we look at the vehicle at high speeds or moderate speeds, right? And last class we were looking at this model in detail, the configuration, and then its kinematic diagram, and then we were deriving a fundamental governing equation for steady state cornering, which is essentially the requirement of steering angle, which is given by function of vehicle geometry and the turning radius. That's exactly what is delta F is equal to L by R, where L is wheelbase of the vehicle, R is turning radius, then L by R minus alpha F plus alpha R is what he had got. Alpha F and alpha R essentially slip angles at the front axle wheels and the rear axle wheels respectively. So this is what is that steady state governing equation that we have derived in the last class, looking at kinematic diagram of bicycle model. So today essentially we are going to look at that again, and with the free body diagram, and we can also get the same equation, and we look at what is the physical meaning of that derived understeer gradient. So what we can do with this understeer gradient estimation of a given vehicle, right? So that is going to give you the tendency of the vehicle during maneuverability. That's what today we are going to understand. And we will also go into pure cornering governing equation and look at the equation, how can that be reduced to a convenient form called a state space form, which is essential for your stability analysis or your transient response studies and so on. So it's very popular. If you look at any automotive vehicle dynamics textbook, especially with the control system combination. So automotive control system textbook, if you look at, you would see that governing equation is essentially represented in a popular form called a state space form. So that's what is that form that we will be deducing our governing equation. So this is essentially what is that in this 45 minutes we are going to do. And let me share my screen for the same. I hope you are able to see the screen of last lecture what we have seen. So steady state cornering of two axle vehicle. So you had to have only one equation, that's force balance equations. So lateral force Fy is equal to MRU, and Mz is equal to 0 because it's steady state, right? So the variation of R dot is 0. Your rate or acceleration is 0. So what's happening when you give a steering, it is only a orientation change with the constant angular velocity, yaw rate. It is not changing with some angular yaw acceleration. So then that state is not called steady state, that's called cornering state, right? that we will see today's lecture as well. So what would happen if I have mz is equal to izz r naught r dot, right? So there is no doubt in this bicycle model. We had looked at very carefully in the last lecture, and you could also see that once again the diagram is redrawn so that you are not having any doubt. So this relationship is essentially obtained based on what is the relationship given by equation 9. Delta f is equal to L by R minus alpha f plus alpha R. This is essentially given by this configuration diagram, wherein we were able to represent the motion parameters, effect diagrams, you can say. There is no forces represented here. It is only the motion parameters. That's why it's called a kinematic diagram. And this angle at the center of turn is what is L by R. So angle subtended by wheelbase at center of turning radius is what is L by R, right? And this essentially is sum of A by R plus B by R. So we were making an attempt to get this expression, and finally we are able to deduce the fundamental governing equation from number 9. So this is a kinematic equation from number 9 we were able to derive as we know these expressions, right? So once again, let us draw. So here the equation 15 is what is final equation that we derived, where KUS is defined as difference in tire compliance in the front axle and the rear axle, right? So WF by C alpha F is what is called compliance, and WR by C alpha R is what is called compliance at the rear axle wheels. And u squared by r is what is your centripetal acceleration, and it is divided by g, so it is g units, right? So here see again dimension. L is what is wheelbase in meters, r is turning radius in meters, so there is no unit. So these all are in radians. So delta f is in radians, and this delta f, whatever that we have, is the steering angle at the wheel, tire wheel assembly. So that same angle is not given by the driver at the steering wheel. So that would have some steering ratio reduction from given input by the driver, which is felt at the wheel. And our bicycle model, we do not have an explicit appearance of steering wheel which is inside the cabin, where driver could have a input through that. Rather, in bicycle model, we represent only the front axle wheels collapsed as a single wheel, and that wheel steering angle is what is requirement given by equation 15. In that, you essentially see a term called an understeer gradient. So this understeer gradient value can be positive, negative, or 0. So let us all discuss that. Before that, let me also show that this equation can be derived through free body diagram. So let us draw today's class a free body diagram and then continue. So this is lecture number 24, and today it is 3/4/2021, and FBD of bicycle model during steady state cornering. FBD stands for free body diagram. So that's for a dynamic equilibrium. So this is for a dynamic equilibrium, right? So our model essentially has this frame represent the length of wheelbase and then steered wheel in the front axle. And the steering the collapsed wheels at the rear axle, and CG location on the frame. So this is our bicycle model. So in this model, what are the forces acting? That you know that the force direction would be in this direction. because this is front axle or front wheel plane, and if I extend this line, and this is our steering angle, steering input. Because of the steering input, you see that there is slip developed. So this slip angle is alpha f. So that's measured in this direction. That's why we take always minus alpha f. Same way at the rear axle, we get alpha r. Right? So if you look at this is actually the direction of wheel travel. That means this is the direction of the velocity. This is the direction of the velocity. So the direction of velocity here is slightly not along the axis. It is also inclined like this that we have seen. It is at an angle. And this component is what is u, and this component is what is v, and this is what is called the body slip angle beta. So this is very clear. I should not I should not feel that you are not following this, because it is all, this entire bicycle model is going to turn about the center of turn. So where is it placed? Somewhere very far away, somewhere here. So if I have it, that is this point, and this should be perpendicular. It will be like this. Just a minute. So it is somewhere here. Where this angle is 90 degrees. So if you see, this is in this direction. So this angle is 90 degrees. Similarly, I would have here as well, perpendicular to this direction, and that would again meet at this point, right? I would have here, and that would be meeting at this point. So this is the center, what is called an instantaneous center of rotation, ICR we call. So this entire rigid body is turning about this point. Then any point on the rigid body, velocity direction you would get if you join that point to this center and draw the perpendicular. That's a fundamental of basic rigid body kinematics. So rotating. So you could also remember that. So you can also see that if I have a wheel, right? So the wheel is hinged here. Bicycle is on a stand and wheel is rotating, rear wheel. Then it will be only rotation. If wheel is bicycle is ridden, you look at the same wheel is undergoing what is that motion called a general plane motion. That means the CG will translate as well as it is rotating. So if that is so, what is this velocity you get? If the surface is rough surface, it is not sliding. So this point is what is called an ICR. So if I have to get the velocity of this point, I should join this to this, and then I see this is perpendicular. This is the velocity, right? If I have to take a point somewhere here, what is the direction of velocity of this linear velocity? How do I get? I should join that to this instantaneous center and then draw perpendicular. I'll get it. So that's the exact thing. So if I take this point, then what is the velocity? How do I get? I should join this to this point and draw perpendicular to that. So like that, in a rigid body, if I take any point, at that point velocity as it is rotating and translating, at that time what is that center is called an ICR. So you join all the point to that, and then you'll be able to draw the vector, velocity vector. That's exactly what is I did it here as well, right? So this explanation I just have given so that any of you are not able to follow what is this, then it's easy for you to get this idea. So this is that. So why did I draw this? Essentially is because that is the direction of your force as well. So now what are the forces going to act? So see, now I would have, as it is turning in a steady state cornering, I would have here a force, and this force is Fy, F, and this force is Fy, R. And these are the forces developed, and as it is a dynamic equilibrium, I would have my inertia vector, and that inertia vector would act in this direction. What direction it would act? At the CG, in this direction it will act. And that vector is what is mu squared by gr, centrifugal force. So in a dynamic equilibrium free body diagram, this is centrifugal force. Otherwise, what I would do, I would have these two force summation, what is my Fy, that is here, and again in another equivalent diagram, I would have this as a centripetal force, right? So this is centripetal force alone if I don't represent any other force, or for a dynamic equilibrium along with an external force developed at the contact path. If I bring in this is called a centrifugal force. It is just directed in this direction, as your centripetal acceleration is in this direction, right? Centripetal acceleration is in this direction towards the center of turn. So this is the free body diagram. So now you see these angles are very small angles. So if this is 90 degrees here, and if I have to resolve this force into two, one perpendicular to the wheelbase, this frame, other one along that frame if I take, and this force is very negligible, this force only I will consider. It is not negligible. When I take moment about this point that is going along with that line will not participate. So I would take a moment equation. So what is this is now? So since this angle is alpha r, this angle also is alpha r. It's very small angle. So this Fy r, so this component is Fy r cos alpha r. So small angle, cos of angle is 1. That's why you take FIR itself. That's why you take FIR itself. So we make an important assumption as what? Alpha F, comma alpha R, and beta and delta F minus alpha F. Already these are small angles, all very small angles. If that is so, you would get like this. So now here you see what would be the component along perpendicular to this frame is this, and other one would be in this direction. So this angle here is delta F minus alpha F, which is again a small angle. So Fy cos, so this force component now is Fy F cos delta F minus alpha F. Essentially, this is going to be 1, as this angle is very small, and this is also is going to be 1, as alpha F, alpha R is very small angle that we consider. So that is an advantage of doing it. So now to get my equation, what I should do, I should take a moment about, let us have front axle, this center as point A, this center as point B, and let me take moment about B, that's equal to 0. And here what is the convention? So if I have, this is clockwise is positive, right? Why clockwise is positive? SI coordinate system. So I'll take this is positive. So when I take moment now about point B, I would have now only this. So similarly, the centrifugal force also, I would have one component goes like this, and other component goes like this. So this component, if we take this component, so that component value is what? Mu squared by gr cos beta. Again, cos beta can be 1. That's what is an advantage of writing this equation. The other component which is there along this axis will not participate, along this frame will not participate in the moment equation, which is sine component. The other component is what? Phi r sine alpha r here. Here it is mu squared gr sine beta, and here it is Phi f sine of angle delta f minus alpha f. So that the sine of angle force component is all along this, in this forward direction along the frame. But I do now take only a moment equation. So what would happen? See that if I have to take moment about this, I will have Fy F, which is this, and that's positive, into L. Fy F into L. And this component you see now, about B, it's negative, right? The counterclockwise, so minus, that is m u squared by g r, right? So where m is w, it's not m, it's w. I'm sorry, this is w. You have to take this as w. It's not m. I divide this by g so that it is become mass. So this is w. W squared by gr into this distance is b, wheelbase b. So that's correct. Is yeah. Into b, yeah, that's correct. So is equal to 0. So I would have now fi. What is FIF? By the way, let us substitute FIF. We had looked at FIF can be expressed in function of if this is alpha slip angle and this is Fy, and the variation goes something like that, and this what is the definition of Fy by delta alpha equals at alpha equals 0 is what is defining C alpha. So if it is that here Fy, this Fy can be replaced by C alpha F into alpha F, and this alpha F I have to take it as minus sign, as this direction measured here is in the negative direction with respect to SI coordinate system, into L minus W B U squared by GR, right? Yeah, so that's equal to 0. So you have now this term can be taken out, and if I bring L, WB by L is what is WB by L is what is WF. So I would have minus C alpha F on the other side. When it goes, it is WB by L into U squared by GR. So that's going to be WF into U squared by GR, and I would have my alpha F is minus WF U squared by C alpha F GR. So this is equation 1. And the same way, if I take a moment, about point A, if I continue with a similar fashion and take a moment about point A, and considering clockwise positive, then I would have Fy R into L, and that is counterclockwise, so minus, and this become clockwise, so plus W A U squared by GR, that's going to be equal to 0. So this, if I replace here, it is going to be minus C alpha R into alpha R into L plus W A U squared by GR, that's equal to 0. So alpha R essentially going to be minus W R U squared by C alpha R G R. So this is equation 2. So now I have my kinematic relationship for this. What is delta F is given by L by R minus alpha F plus alpha R. Substitute. So put 1 and 2 in this equation number 9. Earlier we have derived, right? 9. So you would have L by R minus alpha F is minus of minus become plus WA U squared by GR, and here plus and here it's minus, so WR, this is WF, okay, WF U squared by C alpha F into GR. So this is WR U squared by C alpha R GR. And this again, we can take this common term out, L by R, and plus WF by C alpha F minus WR by C alpha R into U squared by GR. This is what is delta F. So this is how also we can derive this equation instead of writing those all kinematic relationship. I have to do both because those relationships are very much essential. You would quite often use while solving problem or important deduction of when you during the derivation you may have to play around with manipulating things up. Then you have to understand every equation you should remember. Like if I say small r into capital R is equal to U, correct? That's very clear. So like that small relationship you should know, which are called kinematic relationships. So here this delta F is equal to L by R, and this is again, this term is what is called the KUS. So plus KUS into U squared by GR. So again, the unit is what I was telling. So KUS would be in radians, U squared by GR. So U squared by R is again an acceleration divided by G. So that is also unitless. So this entire thing is given in radians unit, right? Yeah. So this is the equation 15 what we have derived in the last period. So you can also do this derivation just looking at the free body diagram or a dynamic equilibrium, and you can very well do this. Now we are going to look at what are the physical meaning of this equation. Why did he derive this equation? So that we will see, and we will have some discussion on it, right? So this equation 15, what do you understand from this equation 15? Can anyone say? From this equation 15, what do you understand? So look at what is on the left hand side, delta F, that is steering angle requirement. So what is the steering angle required to negotiate a given curve is what is given by this angle, this equation 15, and that is essentially depends upon wheelbase, turning radius, and the vehicle speed. That's vehicle forward speed. This U squared is what is U is what is the vehicle forward speed. Or you can say this together, U squared by 2R as a lateral acceleration. Either vehicle speed you can say or lateral acceleration you can say. So, and of course with this KUS. So these are the four parameters. Decides what is the required steering angle when you are going to take a turn. So what does this KES depends on? This KES is function of what? You have seen KES is WF by C alpha F minus WR by C alpha R. So what is WF and WR? It is the load distribution or weight distribution, and what is there in denominator? Cornering stiffness. So this understeer gradient of the chosen vehicle is function of weight distribution and cornering stiffness of the tires. Look at this, very important. You should understand this. Right. So now let's look at different scenario cases. So case 1, I would say that this vehicle handling behavior is neutral steer behavior. Neutral steer behavior. When vehicle is tendency is called neutral steer behavior when this KUS value equals 0. When this KUS value is 0. So when this KUS value can be 0, can anyone answer? When this KUS value can be 0? So look at here. This. So when this KUS value is 0.
WF and WR are equal.
WF and WR are equal. That's only sufficient. You look at the denominator as well. If we have WF is equal to WR, but the C alpha F is different than the C alpha R, what will we do?
Alpha F equal to alpha R.
Yes, excellent. So you should have alpha F is equal to alpha R. Alpha F should be equal to alpha R. So what are these alpha F and alpha R? They are essentially a requirement for your cornering force development. That is called the slip angle, right? So slip angle in the front axle wheels tire contact and slip angle at the rear axle wheel tire contact. So if these are equal, then that vehicle is said to have neutral steer tendency or neutral steer effect. So what do you mean by physically? What do you mean? What would happen to a neutral steer vehicle? How can you physically understand this? So one is the requirement. Now the requirement has become what has happened because of this. What has happened to the requirement of your steering angle? So KES in this equation 15 it's 0. So what would happen? It's only L by R. So is L is going to change in your vehicle? No. So R is going to change. It can change provided you have your value here. So this R is what is the turning radius. So let us assume for our case study, R is happens to be some 30 meters. Right? L happens to be 3 meters. I am taking a long vehicle, right? 3 meters and 30 meters. So now what would be my steering angle requirement? It is 3 by 30. It is 0.1. What is the unit? Radians. 0.1 radians. So what do you understand by this now? If my vehicle, you have your 3 vehicles in your hand, digital assignment. If the 3 vehicle has got your understeer gradient 0, what do you mean by that? So how do you understand? That's what I was just explaining you. It depends upon 4 parameters. So let's just look at that in a graphical representation. So for that, let me take my requirement of steering angle in vertical axis, and I'm going to take on this vehicle speed. It's the function of speed. So now look at the neutral steered vehicle where KES is 0. I have my steering angle L by R on a given radius 30 meters. So what do you mean by that? What is the steering angle requirements? I have a constant value here. So irrespective of the speed of my vehicle, I do have a requirement of my steering angle is fixed. What I mean by that, I have my vehicle taken inside the test track of 30 meters radius, and once it is gone and the start point of my measurement is what is that particular constant speed, or in sequentially I will increase the speed. It is not I am accelerating my vehicle along that, then it is not steady state cornering, right? Steady state cornering means what? You are driving your vehicle with the constant forward speed. So your vehicle would be taken to the test track with the requirement of speed. So as it is entering the circular track tangentially, that speed requirement of your test would be gained. So it is say 20 meters per 20 kilometers per hour, 30 kilometers like that. If it is incremented, it's 20, 40, 60, all in kilometers per hour, right? So I would take my vehicle with this speed and I would see that my steering angle required is not changed. I go with this speed again in a circular path, the steering angle is the same. So that is what is can be measured. So that would happen if your vehicle is behaving with the neutral steer effect. Your front wheel axle slip angle and rear wheel axle tire slip angles are same. So that's what you understand by this value KUS is equal to 0. So this is now 80, 100, 120, like that. Any vehicle speed that you go, right, 140, 160, you would have the requirement of steering angle given input is fixed. That's what is neutral steer vehicle. So this is That you understand. So what is this value for this chosen case? It is 0.1 radians. So in degrees, if I have to say how much it is, how do I find out? It is 180 by pi into 0.1. So for pi radians, it's 180 degrees. So into 0.1 radians, how much if I find? It's around 5.5 degrees something. So that is what is that happens in this, irrespective of that steady state speeds. Right. So how do I get this? Is I'll get this all marked for a particular speed. What are this value like that? And then I just join them all by line. It is not accelerating the vehicle on the curve, right? Yeah. So that is what you understand. So now, in case this KES is not 0, then what would happen? If case 2, right? In case 2, KUS is greater than 0. So what does then your when that can happen? It can happen when your alpha F is greater than alpha R. So front wheels slip angles are greater than rear wheel slip angles. I will have my KES understeer gradient positive value. So if it is positive, then what would happen to it? So this is my equation 15. You look at now, delta F is equal to L by R, which is constant part, which is here, and plus KUS into U squared by GR. So look at speed here, which is square term. So the variation of my requirement of steer angle, as I have my sequential step speeds increased, would have variation parabolically. So if I see that at 20 kilometers per hour, I would have some value here. In 40, I would have some value here. Requirement of steering angle is increases. As my speed increases, the requirement of steering angle also is increases. So like that, if you see, that would go like this. Let me just take all of them here. So that would go like this parabolically, right? Parabolically. So you see that gradually the steering angle requirement increases as you go with your vehicle. So that is the meaning of this. Case 3. KUS is less than 0, that will happen alpha F is less than alpha R. So what would happen here? Delta F is L by R plus KUS become minus KUS into U squared by GR. So since it is minus here, as the speed increases, what would happen? The requirement of steering angle would be subtracted from this 0.1 radians requirement for a case of this neutral steered vehicle. This is understeer vehicle, and that would again change, and that variation would be coming something like this, and it is going to intersect here somewhere. All right, it's going to intersect somewhere here. So this is what is for oversteer vehicle. See, look at now, very interesting. In one case of understeer vehicle, I require my steering angle to keep increasing. On the other hand, for an industrial effect of vehicle 0.1, but the steering angle reduces. At one point, the steering angle is 0. This is 0. This speed, I don't require to steer at all. What do you mean by that? What do you mean by that? Can anyone answer? So there is particular speed where this graph crosses this. So I don't require to give my steering at all to my vehicle, but vehicle do have yaw motion. So what do you mean by that? Do you follow that?
Yes.
Yeah. What is it?
So the rear of the vehicle leaves the traction. That is the point where at which the yaw motion continues, but we do not have to give the steering angle.
You do not
Oversteer.
have to give the steering angle, or your steering means you give or don't give. No, that is out of control. You cannot have the steering control. So you don't give the steering also. No, that is happening. So this speed is what is called a critical speed. U critical. critical speed. So when there is steering requirement is 0, right? And you see here, similarly, there is a speed called a characteristic speed. So if this is 0.1 radians, I go to 0.2 radians. So when I require my steering requirement is double that of a neutral steer effect, and what is the corresponding speed? I would call that as characteristic speed. So there are two definitions. A steering angle requirement for a characteristic speed is that when the steering angle requirement is doubled as that of requirement for a neutral steer vehicle, then that speed correspondingly, what is it called, is characteristic speed. If the speed is 0, critical speed, when the steering angle requirement is 0, then without any input, steering input, you see that your vehicle would have the yaw motion. So you don't steer, it is having on its own means, what is that? Driver is not giving any input, but vehicle doesn't listen to the driver, so it is an unstable state. So you can have your vehicle which can be oversteer vehicle, but if you go to the speed which is critical, at that time you cannot have any control. So till here the reduction in steering means what? The input driver, whatever he gives in a neutral steer vehicle, what steering input that he had, when you take a turn, normally our vehicles all are understeer effect, so we increase the steering. But in case of an oversteer vehicle, if we could have driven the vehicle, you would have done that. Otherwise, you could see that in Formula racing and all, where the racing cars are designed as an oversteer effect to have a sharp turn. So whenever there is a turn, instead of steering to the turn, there would be a counter steer would be given. So what do you mean by counter steer? The reduction in the steering. So as I have to take my turn, I have to reduce my steering is what is the tendency of oversteer vehicle. So the reduction is keep reduces, but vehicle speed is critical speed. Then you can't reduce anything further. So that means that is the point where the vehicle get into an unstable state. So driver steering exercise is completely lost. So every vehicle, if it is an oversteer vehicle, that would have what is the corresponding critical speed, and that speed should not be driven in cornering, right? So that's what you understand from this equation number 15. So you can also look at that in a very physical perspective fashion, right? So I'm going to look at my vehicle itself in a turn. So we have just chosen this turning radius is 30 meters. So let me accommodate in my board, and this is my turning radius R 30 meters. In this I have my vehicle now. So this is my vehicle. I just put a skeleton of that. And I have here a wheel, here a wheel, I have here a wheel, and here a wheel. So I could bring in my wheelbase and I could bring in my track, right? So this is my vehicle now, a simple sketch. So now with respect to this, how can you define your tendency of the vehicle from this equation? So in first case, what has happened? First case, it is a neutral steer effect. So neutral steer effect is the steering angle is fixed. So if you see that the neutral steer vehicle means this would go in the curve exactly. So you'd see that the vehicle turn will be along the course. It will not deviate from the course. What do you mean by that? The turning radius does not change. That's what you see in case 1, neutral steer effect. Delta F is just L by R. So L is not changing, R is not changing. That means what? Every time the orientation change is such that it would be along the course exactly. That's what is neutral steer effect. In case 2, which is understeer effect, where you see delta F is increases as U increases, speed increases parabolically. So the variation is parabolic variation. So what would happen another way to say here? What would happen with respect to turning radius? The turning radius would increase as this delta F requirement increases, speed increases, the turning radius also would increase. So your vehicle would have its motion, the CG, just keep increasing with this radius. So this would be understeer effect. See now, This point it is R. If I take this point, that the center is not changing. So the radius, turning radius keeps increasing. So the turning radius to be constant, what does that is required? You are supposed to give your delta F. You have to give the correction steering. So you have to steer more to bring this US like this. So the increase in R to compensate, you are supposed to do. So that is important, right? Your test vehicle has to be tested on 30-meter track, and your vehicle is understeer vehicle. You do not correct your steering. You hold as if it's neutral steer effect. It's 0.1 radians only. The vehicle radius keeps changing and it will go out of the track. So that is what is physically would happen if you are observing from the top view your vehicle. So the steering would be given so that it can be always brought into the curve. So on the other hand, case 3, oversteered vehicle, what would happen? Delta F is requirement is decreases as U increases, and the turning radius also would decrease, right? So turning radius, if you see, if it is an oversteered vehicle, it would reduce like that. So this would keep reducing it, but I don't want to go here. So my track width is there here, the road track width. So it should not come inside, it should not go out. So I should be accordingly to have a correction. So that is the meaning. So you could say that no, it's better to say that instead of a steady state, if I have my vehicle, if I accelerate like that, you can say. If you go with the steady state speed, you are giving the correction. That's what is in this graph you say. In case you are accelerating your vehicle on the curve of 30 meters radius, if the vehicle happens to be neutral steer vehicle, what would happen? Irrespective of the speed, it would go in this. That's what we understood from the graph. If the vehicle is of understeer vehicle, you accelerate your vehicle. That means you are varying your speed. As the speed varies, what would happen? Understeer vehicle, the radius R would also increase. That's what is the meaning of this. If the vehicle happens to be an oversteer vehicle and you are accelerating a vehicle, right? The word I am using, accelerating a vehicle, is not correct for a steady state cornering. But in case you are accelerating your vehicle, that speed is varying continuously. As the speed varies continuously, oversteer vehicle would go with the reduction in this radius. That is why you should give a counter steer. So that's what you should understand this, right? So this all when you are accelerating your vehicle on a curve, physically what is happening to discuss. So when the vehicle is accelerated in a curve, then these are the three cases. So what is happening to the turning radius is what is from this understeer gradient you are able to see. So you can also look at this in another perspective. So this is the vehicle which goes in a curve. If the vehicle is going straight, what would happen if they are acted upon by sudden side force, right? So let's look at the vehicle. Let me draw the top view of my car. And I have here a wheel, here a wheel, here a wheel, here a wheel, and this is wheelbase here, right? And this is the top view of my car. So if this goes straight now, so this is my longitudinal direction. The vehicle directed along this, it goes straight. What would happen to this vehicle if there is a side force that is acting? Right? There is a side force that's acting here, Fs, due to wind gust. So what would happen to this vehicle if this vehicle is neutral steer vehicle or understeer vehicle or oversteer vehicle? Can anyone comment on this? if this happens to be a neutral steer vehicle, the slip angle developed the front axle and the rear axle wheels are the same. For the side force, what would happen to this vehicle? It goes in the straight path. What would happen to this vehicle? The direction of motion would slightly at an angle to this path, and it goes in a straight line. It goes in a straight line, but with some angle, right? This goes in this straight line. So this is neutral steer vehicle effect. If it happened to be an oversteer vehicle, what would happen? Oversteer vehicle would take a turn inside the external side force. This is oversteer effect. So it will go like this. If my vehicle goes straight and suddenly I have it, and this vehicle speed is so high, maybe closer to not to critical speed, closer to that, side force is acting. Oversteer effect would be get into the force. If it is an understeer vehicle, the force acting, it will go away from this. So your correction would be to the side where the force is acting for an understeer vehicle as well as neutral steer vehicle to have it in a straight direction. Whereas oversteer effect vehicle you drive, you will get your wind from your right side and you have to steer to the which direction? You have to steer to the left direction. So that is the meaning of your understeer, oversteer, and neutral steer effect here. Right? So can you just find out what are these V characteristics, speed and V critical speed? How do you get it? What is the value of this? So that's what we said, delta F requirement should be equal to 2 times of L by R. What is there for a neutral steer effect? And here delta F requirement becomes 0. So that's a corresponding thing. So if this I follow to get my V characteristics or V critical, I would take my equation of delta F, and in that I would substitute in place of delta F 2L by R, and this side L by R plus KUS into U squared by GR, right? So this comes on this side, it's L by R, so my U would be how much it is? My U would be, I require this, so this comes here, it's L by R, so U square by GR here, on this side it's L by R by KUS, because this brought down and GR goes up, so this becomes U square is equal to LGR by R into KUS. So RR goes out. So I get my U characteristic would be under root of LG by KUS. So similarly, V critical, how can I get? In equation 15, delta F 0 is L by R plus KUS U squared by GR. So my U critical would be under root of minus LG by KUS. So this minus sign comes here, minus, and KUS value is negative, minus minus goes up, I get what is my critical speed. So this is an expression for critical speed. So you should know this, which is useful for calculating a characteristic speed of your vehicle chosen and critical speed of your vehicle chosen, right? So this all are something that we understand from equation number 15 and equation number 19 essentially, 9 essentially, right? So now let us look at another set of equation for pure cornering. Do you have any doubts so far what we discussed? Do you have any doubts so far what we discussed?
No, sir.
No. So I think it is time up, right? So you have a class at 9 o'clock. Let us stop here, and tomorrow we will go with the next pure cornering governing equation set, and then we will deduce that to a state space form, right? So if I start, it would require another 20 minutes. So let's stop now, and we'll continue our class tomorrow morning again at 7:30 as usual. Is that fine?
Hello, sir.
Yes, sir.
Yeah. You have any doubts, you can ask. I would answer. Otherwise, you can leave for the next class. I download that minutes now. Yeah, some of you called me. Any doubt? Yeah, Deepak Narayanan.
Sir, in a real situation, like irrespective of steering input, like say we have a constant steering input,
Yeah.
and keep on increasing the speed, like I'm accelerating for a constant steering input, then there
Yeah.
won't be a constant turning radius, no, sir. It will vary, right?
Yeah, it will vary. If the variation is increases, your vehicle is understeer vehicle. If the variation is decreases, right, the radius variation is decreases, then it is oversteer vehicle. Even there is no variation, you are in a test track, you go with your vehicle and you accelerate it and you have the same steering angle, then the vehicle tendency is neutral steer vehicle tendency. In general, reality, you say no, our all passenger cars are designed to have an understeer effect, so that for a safety point of view, that's good. So you will never lose yaw stability, right, even at the higher speeds. But yaw stability lost can also happen due to braking that we have seen. So when you do a hard braking and then it happens that rear wheels lock before front wheels, what would happen? There is lateral force developed at the rear of the axle is not sufficient to hold the tires, rear wheel tires. So it would turn about the yaw center with respect to front wheel axle point. So you see suddenly your vehicle go unstable and you can't have a steering control. That would also happen because of braking. You are asking about the acceleration. So as you accelerate, your vehicle will go unstable state if the speed reaches the critical speed, what way we have seen. On the other hand, if you are braking, the braking is such that your vehicle doesn't have an ABS, and your brake force distribution is not an ideal brake force distribution. What would happen? You would see that there can be a chance that rear wheels locks before front wheel. That can take you to an unstable state of your vehicle. So this allows something stability of vehicle in top view, yaw plane motion. Do you follow Deepak Narayanan? Did I answer your question?
Okay, sir.
Yeah. Any doubts? Vineet Krishna is there?
No doubt, sir.
No doubts. Okay. Anybody? Any doubts? If you do not have any doubts, good day to all of you. I know it's very hectic, even Saturdays we have today, this week, last Monday, holiday, make you all to again to have these lectures. But it's all part of our life. Of course, it's for benefit of learning. We have this additional instructional day. Good. Tomorrow morning, let's meet. And we will go ahead with looking at representation of bicycle model governing equation in a steady state, in a state space form, right? Okay.
Sir, tomorrow morning or Monday morning, sir?
Oh, okay, so I mean tomorrow means next instructional day. I'm sorry. Tomorrow,
Okay, sir.
Monday morning 7:30. Tomorrow, Sunday, right? So Monday morning 7:30 we'll have next lecture. Okay. Okay, Rani, Annapurnesh.
Okay, sir.
Okay, thank you. Bye.